Welcome everyone, and so to our last guest lecture in the fourth semester. Today is our great pleasure to have Dr. Saranya Anbarasu from Jacobs Engineering to introduce the modelica modeling for the smart and connected communities. Saranya did her PhD at Penn State. She just graduated recently. So this is part of her PhD thesis. So without further ado, Saranya, you can start your lecture.
Sounds good. Thank you, Dr. Zuo, for this great opportunity. I've been watching all your previous lecture series as well. It's been like really, really useful. And then, for anyone from the industry or at academia, it's just like, good resource to look at. And thanks everyone, whoever has joined this session. Looking forward to, present my work on smart connected communities. Just give me a moment. I'll share my screen. Is my screen visible
Yes.
to everyone? Okay. Thank you. Thanks all. Okay. I just want to give a quick background and thanks Dr. Zuo for introducing as well initially. I'm an architectural engineer. So I did my master's and undergrad from India, from CEPT University in India. And I did my PhD in architectural engineering from Penn State with Dr. Zuo's lab, Sustainable Building Systems and Societies Laboratory. And over my time there, I did get a chance to work on Medallica-based modeling for a few DOE and NSF projects, so which included optimal co-design for integrated, thermal, electrical, and control systems for grid efficient and interactive districts. So this was focusing on modeling, the systems, district systems for CU Boulder campus, and was in collaboration with multiple institutions, where I did focus on modeling the heating system, which were steam based, and the power system, that includes cogen and the others, and also did support template model developments for Endel's UrbanOpt as one of my projects when I worked with at SBS Lab. And also the other interesting one is the NSF's big data collaborative research. So this was using big data and also using Medallica to optimize planning for smart, sustainable, and connected communities. This was in collaboration with Virginia Tech, so which is what I would be presenting today. And right now, I'm working as a district energy engineer, which at Jacobs. It's within energy and power division of Jacobs. And I've been working on developing models, doing transient modeling, simulations, and analysis for data centers like cooling and power systems. We've been doing a lot of resiliency studies, understanding how the disturbances hits these systems and how we can quickly recover back. And also the geothermal thermal energy networks, which is the focus, like everyone is talking about it, decarbonization, right? Like, so this is like where we are trying to leverage earth as a storage medium and to buffer out all these load spikes and other things, and then trying to work on projects as well. The presentation outline, it's going to be the big data collaborative research, where this entire project was focusing on the framework for developing, smart, connected, and sustainable communities, where the objective was to have zero emissions, zero energy, zero outage, and zero congestion. So those were the goals for optimized planning. And there was this project focused on developing a framework that can help you decide how, when, and where to deploy and upgrade these community infrastructure systems. And that's what I'm going to present today. And few other things down the way, it's like we want to talk about the mega trends that causing challenges to the infrastructure, what are interdependent infrastructure, and our modeling approach to model these interdependencies. And the Medallica library that stemmed out of this research is also I'll be presenting that. And three different case studies of using this modeling library, and also some future extensions and ideas and opportunities that you can use this library for. So these are, as everyone knows about these global mega trends, the challenges, which includes the urbanization, climate change, digital transformation, energy transitions. Like we talk about electrifications, and then we are taking lot of efforts on that, and also the resilience, which is very, very critical when we think about these, huge smart communities and cities. And as you see, these challenges pose stress on these critical infrastructure systems. And most of these critical infrastructure systems that you see on the right are often treated as individual systems. Like we do modeling for energy system, and then we just treat it as one entity, right? But these are actually interdependent systems where there's more interlinks that are connected. Energy systems are connected to transportation. There's connected to communication for dispatching and economic dispatch of the generation assets, and a lot more in water distribution, socioeconomic, and human behavior. So all these are highly integrated, and often we miss out understanding that these systems are integrated. And if we want to model a robust system, design a robust system, then we have to model interdependent community. That's how we can get to. So just to give a quick, example of what all systems we are considering in this study. So we have the energy system, and it includes all the energy infrastructure, the power grids, power plants, distributed generations like PV, wind turbines, and there's also building demand, district heating, and a lot more. And then there's transportation infrastructure, which has like roads, EVs, there's signaling infrastructure, and wherein the EVs are supplied by the grid. And on the other hand, there's communication, which includes the towers, data centers, smart communications inside smart homes, and like a lot more like SCADA systems for districts. So these need also power, and also the communication systems support the trip management for the transportation, or energy dispatch at the power generation. And there's water networks, the other infrastructure, which is also critical because they serve for support the power generation, and in turn also need power for distribution. And overall, there is this humans who are interacting with these infrastructure systems, and they are the one who change the behavior of how much we're consuming. Like how much power are we going to consume for the EVs? Like when do we charge it? When do we discharge it? When are we going to consume electricity in homes? So all that is all dependent on how humans behave interacting with these infrastructure. So it's highly critical to trace all these when we're modeling. To give you a quick, literature, this is from literature. So it's about like what are interdependencies. It talks about a study for a couple power and communication model for a Polish power system test case. So if you look at just to understand setting a base of what interdependencies are, I'm bringing out this example. Um, so we have the communication system and we have the power systems. So say each power system node is connected to one of the communication system node. So if one of the power system node fails, and it's going to affect the corresponding node at the communication, and probably it might affect the other two links that are connecting those communication nodes, and also two links in the power. So this is called as a couple topology, or just the topological or physical integration. And in real systems, it's not going to be one node fails and the other node just fails, but it's going to be the one node. Say if it is going to be the electrical system, failure in one node is going to cause more power flowing through the other lines, and then the lines can withstand only a limited amount of power to flow through them, and that will start heating up, or that will start going into blackouts or brownouts or anything. So that can start cascading into it. So when you look at before cascading and after cascading, this is like a network for a city scale, where you see if you just treat only the physical interdependencies as the connections, you're going to just see corresponding nodes failing in the communication system or power systems. But then if you're actually considering cascading, you see separated islands over there, where each island is going to have different levels of failures. It's going to be having different issues. So this is what we want to capture. But these studies are pretty much done for large city scales, and they focus on vulnerability studies, existing studies and literature. But we also want to think about like normal, stressed, and restorative operations, what happens, and then also in community scales. And then most of these earlier studies focus on like either one of the physical connections or physical and cyber, but not many focus on all the three types of interdependencies. And also there's limited integration for multi-domain systems, like there's only 2 or 3 systems coupled, but not the multiple systems integrated together. And also I said, like, there's limited research on um, beyond topology, not just nodes and links. We have to focus more beyond that. So it's like there's functions happening, right? Like, say, if there's power line, if the power lines are overloaded, there's going to be change in voltages, there's going to be change in frequency. So that's what we want to focus on, rather than just saying, the node fails, the system fails. So here is what our study focuses on developing to support this kind of a coupled infrastructure modeling. Here, we name this approach as 3M, which is multi-layer, multi-agent, and multi-block, as you see. So the first one is the city layer, which is the topmost layer of the community, where the entire city where there's multiple community blocks in that. And then there is block layer, where you have, block A can be residential, B commercial, and then each of these blocks are going to have the energy, there's communication, there's transportation, all these individual systems at the block layer. And then at the agent layer, when you open out these, the energy and communication or transportation, you see all the individual assets in them, right? Like, say the power grid, or the communication towers, the storage and batteries, all the demand. So all that are going to be the lower level agents. And together, we also did this topology plus the function. So it defines both. We connect the system, also trace the functional relationship between them. Here is one example that I want to show, where we have, let's consider a small community which has one residential block or district, however we want to call it, and then one commercial district. And as we open out, as you all have been aware of Medallica being this hierarchical modeling language, where you can start building out components, subcomponents, subsystems, and so many other things, and then integrate them into big systems. So we are just opening out from the bigger to the smaller scale. Here we have the entire residential district, where we have the supply block, there's demand, and there's a battery to support this community, and also a battery controller that you see. When we open out the supply block, we do see the renewables that's considered in this library and also in our study, but it can be a lot more, right? Like, we can also have a CHP modeled in here. We can also have any other fuel cells or anything that we want to focus, right, for this community. So we can model them over here. So this does have, like, all these models are leveraged from buildings library. So current these models do support the latest versions of buildings. And we also have small step down, step up transformers, and then power lines connecting from these generation assets. And then we open out the demand block. It can be modeled in many different ways. Say we just want to model a simplified community. We can model the demand as load profiles, which are time series inputs. And then the battery controller, which here is modeled as different states of battery, where we can go from charging cycle to discharging cycle to standby cycle based on, what's the supply and generation, net supply and generation. So as I said, the demand model, right? We can model for many different uses. So either we can do simple demand as the previous slide, or we could also model it as a standard microgrid models. So here, one example here is showing us IEEE 16 node feeder. And this has like 3 buses, and there's like loads connected to it and different lines connecting each of those loads, and which has been implemented as a model, connected by loads and all the buses, 3 buses that we see. Or we can also, if we want to do model a real world community, it can be also modeled, just replacing this block with the real world community block. So here is an example of real world community called as Historic Green Village, so which is a community in Florida. And then some of the parallel work from this library done by Dr. Sen Yuang and Dr. Jing Wang. So this focuses on a community which has multiple buildings, heat pumps, domestic hot water networks, and this it's connected to grid and PV systems. So where the figure here that shows all the thermohydraulic networks with connects the heat pumps, pumping stations, and also there's outputs from these heating elements and cooling elements to the power grid as well. So it's more like a holistic real world design model, demand model. So once we have the energy systems, we also did model the transportation, communication, and water networks. These are the other infrastructure systems, but pretty much, these are not the domain. Not we don't have enough domain knowledge. We ended up going with a lower order and lower level of details in these models. But still, we captured all the power dynamics of these infrastructures, which I'll can talk about as we go further slides, talking about interdependencies. So interdependencies, as we already have been like talking about, it's the physical, cyber, and logical relationships. It can be like a first order, it can be a second order, or we can have like a cyclic dependencies. So what because we don't know what all exist, we ended up making a matrix of all the possible combinations, right? Like for energy systems, water systems, transportation, what all the systems can be connected as physical, cyber, or logical. So we ended up listing out everything. And then we figured out, mathematical relationships for few of it that can be modeled, like few of these relationships. So that's what I'm going to talk about now. Like some are very direct, which includes these physical interdependencies, where you see the power distribution network where the lines become these physical connections or interdependencies. And these are modeled with the AC power flow functions, which includes power, voltage, power, impedance, is like real and reactive power and a lot more. And then the model was also validated with the literature. And then we were like very closely following with the standard microgrid implementation on performance. And we also had other system indicators outputted, like it was like the peak valley high and low ratios, and then load coverage factors. There's like line and bus safety factors. So all of these were also can be output from these models. And to give an example, say there's this outage in one of these lines in the microgrid. Say the line 6 has failed or something has happened. And what do we observe? So here is a plot that shows, because of removing one of the lines, we do see the line losses increasing among all the lines. And then there's also voltages increasing, the percentage of deviation started increasing. So same way when we looked at these, the safety factors for bus and the lines, it also started increasing slightly above the standard conditions. So once so many lines fail, we're going to see overloading in this entire IEEE network, right? So that's why these models are going to be useful. And the next direct, the physical connection is the roads. Here, what we did, we want to have the movement of people from one block, as one community block to other, and that will be supported by the roads. And the roads are modeled not just like flow of traffic, but similar to how a pipe has a resistance, we also have the vehicle travel delays, right? So the road models are modeled as, there's more empirical relationships from literature that we traced. And then, based on the average vehicle velocities and flows, we can estimate what's going to be the travel time in these roads. And similarly, this was also validated. And to give a small example, so say there's residential, there's commercial and residential blocks, there's roads interconnecting them. And the plots here show this average vehicle flow during these peak commuting hours. So you can see, the roads which are connecting the residential to commercial, because they have to commute to the offices, we are going to see, larger vehicle flow. And because of larger flows, we are also going to see vehicles slowing down because there's this threshold capacity in roads, right? So that's what we were observing in these road models. And the blocks here that you see are the charging stations. So based on the number of vehicles entering these charging stations, we are going to consume equivalent amount of energy for charging. So that's how these models, the charging model is set up. Similarly, the cyber interdependency, which is modeled as a packet loss model, where we do have data transmitting from one residential block to other or commercial blocks, right? So based on the bandwidth of the network that we are transmitting, we are going to see some kind of a loss in data, which is the throughput. And so not all the throughput is going to make to the other block. And in each of these, blocks, or the communication towers, the ones you see here, these calculate the power consumed for transmitting so many packets between each blocks. So that's calculated by these relationships, and it also includes transmission distance in their equations to assess like how far you transmit, how much you are going to consume. Other interesting cyber interdependency we traced was like, the vehicles are going to be traveling on roads, and then if there's going to be congestion happening on the roads, there's also going to be large number of packets that will be transmitted from those roads, and we are also going to see some packet losses happening. So that will be a larger packet loss. So we also included another, communicative roads where the travel times are going to be extended further because of these losses in data packets. So that's another interdependency we traced. And the third cyber interdependency was signal delay, which is very, very common, right? Like say you're sending some signals to the controllers, or if the bandwidth is not supported enough. So we're going to see some delay in signals on how these controllers are going to, and then that will impair the controller actions. So that interdependency was traced by a delay time that's based on the communication theories that's based on Little's theorem. And it includes these, queuing delays, transmission delays, propagation delays based on the network traffic intensity. So we're going to see different delay times for different networks like Wi-Fi, or if it is LAN, you're going to see a different delay. And we did plug in those delay, components into one of our load sharing controller, right? You see here for the batteries. And then we were able to see, as you see in the plots, because of the delay, communication delay, we are going to see the total energy consumption offsetted by a little factor over here. This shows it's essential to be included in the modeling. And the last type of interdependency is the logical interdependencies, where it focuses on how humans interact with these infrastructures, and how movement of humans across these blocks are going to change the energy consumption profiles of these blocks themselves. And this was modeled as a degenerate Markov chain, which is more like a matrix, and then it can be stochastic or deterministic, which just helps better defining things realistically. And we did observe similarly, like when there's larger occupants staying in the block, we were seeing larger power consumptions, and then the EVs are also based on like how many people leave the block, that is converted into EVs moving on the roads outside those blocks. So that was also seen in these plots. And the way to tie up the occupancy to the loads, we ended up like calculating an occupancy factor or ratio for each of those blocks, and then tied it to the building loads, because building loads, as we know, that a part is like a climate dependent loads, and then a half is occupant dependent load, not half, like a small percentage. So we can, we did tie up that based on the occupancy factor of this entire block. And then the communication electricity consumption was also dependent on how many people were there in the block, how much data they started using. So all that was tied up. And the next one was, EVs, which are very critical components of these smart communities, because the future is going to be electrified completely. And deciding when to charge and discharge is another behavior decision. And that was modeled as a linear and logistical probability model, where people were responding to the state of charge of their EVs, and also the electricity pricing of whatever they're seeing on the community block. So that one we did model as functions. And also we wanted to model the EV battery dynamics, but modeling the entire EV is not feasible for this project. So we did come up with a different approach to do an aggregator, which is a community battery aggregator. So where the entire the community battery capacity is just modeled together, and then the charging probability determines how much the battery charges, and the travel distances, for all the EVs entering those blocks will determine how much power is discharged from that aggregated battery. So that was how we model. So which is more like a simplified approach instead of modeling the detailed EVs. So here we were able to, when we simulated it, based on what is our electricity price that you see in this plot, the middle plot, and then based on what is the state of charge in the EVs, we were seeing different charging decisions made by the people. So it was, when the power was, the prices were really high, we did see the charging decisions, like, no one was charging. And then when the state of charge was high, there was also seeing no one was charging, the green line that you see. And then when you had both the power prices and the, state of charge low, we started seeing more charging happening. So that was how the logical interdependency was modeled. So together, overall with all these infrastructure, individual systems that you see here, we have energy, transportation, communication, with all their interdependencies, traffic theories. So all these are, put together as a smart communities library. So that can be found in these development sites, version 1 and 2. Version 2, we are soon to do an open source release. Final cleaning up, things are happening. And we also have, like, coupled systems listed in these libraries. So we can have, you have standalone models for energy transportation coupled, 3 coupled systems, there's 5 coupled systems. Some of the case studies as well is also available. Uh, so now let's quickly look into the applications of it. Where are these going to be useful? So we did like 3 different scales of work. So one was, looking at the, applying it for 2 systems. One was the energy water nexus, and then applying it for 3 systems to evaluate the different interdependencies, and then, enforcing that, that this is necessary for modeling integrated communities. And then the third one was modeling the 5 coupled infrastructure. And then here we did explore the effects of these interdependencies and isolated which are most critical interdependencies for communities. The first work was just considering 2 systems. As we know, the water consumption processes from sourcing, treatment, distribution to the wastewater treatment. That's more than like 12.3% of the entire energy consumption. And among these different processes and water distribution, we did see the distribution alone is the highly energy intensive process that consumes around like 1,000 to 1,300 kilowatt hour per million gallons. So we wanted to focus on to assess the potential of water distribution networks if they can provide demand responsive services for the electrical grid. And for this one, we did 2 control approaches. One was like the regular typical tank level based controller hysteresis approach. And then we also did a demand response pump control where we were trying to set the controller, optimize the controller to follow or respond to the electricity pricing. So we did take the time of use as well as the critical peak price, and then saw how the pumps were, responding to it. And the demand response problem is a typical optimization problem where we did have a day ahead electricity price and then calculated the pump power over the period of 24 hours. And we also had the constraints such as tank level, demand constraints, pump bounds, and a lot more. And 2 or different optimization methods from the DRL's optimization library was used for this work. And it was like simplex method to evaluate, like, to observe if we are doing load shedding and energy efficiency, and then a genetic algorithm to see if we are doing shedding, shifting, and energy efficiency. And then these had different tuners like variables or constant mass flows. And just to quickly show, this was how the system was set up, like the model, the water network, distribution network with 160 residential units. And there was control set up, demand profiles loaded, and quickly showing a snapshot of actions, how much we saved. So, the table list the comparison between the tank level based controls, the demand response responding to time of use and responding to critical peak price, we were able to see around 29 to 28% savings in terms of energy. And then in terms of cost, we were able to see, from the baseline, the tank level based controls, we saw that the time of use was saving up to 27% of cost, while the critical, when we were, optimizing for critical peak price, we were saving around like 23%. So if you see these, patches here with multiple dollar signs, these are the high price periods. So we do see, other than this red line, all the other, the optimizer is just trying to make sure we don't do pumping at this time. So that was a study. considering two infrastructure systems that was using the SEC library. The next one was the three-couple system, where we did a case study where we evaluated the interdependencies of different systems. And for here, what we did, we took three different cases. One was just the energy systems alone, all alone. And then we integrated the energy and transportation systems. That case three was energy, transportation, and communication. So this was considering a hypothetical community block based out of Denver, and then it has two residential blocks and one commercial blocks connected by the power lines, roads, and then there's transmission cables. All that is how we have set up. So we went from a total, completely disconnected community, which was a baseline, to a completely connected community with three integrated systems. And this is a 100% electrical community, so there's no fossil fuels considered in this work. Here is how the energy, the total energy consumption of the community was looking like for a 24-hour period. So we do see, the case three, which was like three-couple system, that was showing lower consumptions during the peak periods, at least, because we are coupling things together. So there's more, traffic on roads. People don't end up meeting the residences, so they don't start consuming as much energy as they have to. So it's all like, it's all linked. It's all a cyclic cascading effect, because of which we were seeing a 7% lower consumption. And what does this mean is that, like, it's going to have a real time impact on the unit commitment or economic dispatch of the spinning reserves. So that will have to be, that will enhance or increase the generations to make the grid stable. And we have to think about all these interdependencies. And the next one was the impact on transportation network, where we have two cases, right? The energy and transportation being the case two-couple system, and the case three is the three-couple system. So what we were seeing is that on transportation network, because of coupling three systems, the peak commute and the average load velocities dropped even further because there was more congestion and lack of trip routing decisions because of the communication packets peaking up all these times. So because of that, we were also seeing like lower, or more travel times on the roads because of average low velocities reducing. So this gives enforces, like, if you want to model these integrated communities, all these dependencies must be considered. So that was what the second application emphasized. And the third one is a five-couple system where we not only modeled it, we also tried to find which is the most influential interdependency among a six interdependency case that we considered. So where we had energy, occupant behavior, this transportation and energy system as listed as multiple cases. And among that, we had a case six, which was the global interdependency or nested interdependency case, which includes all these systems, interdependencies together. And this is a small schematic of how the community blocks are connected and all the functions and topological and functional relationships that are traced. The modeling approach was similar, like, as we talked about initially. So it's all the same set of models. And the second step, what we did here was to do a Monte Carlo simulation. So this was to understand the sensitivity of each of these input interdependencies. And for that process, we did take in multiple probability distribution. We used them as inputs into our model, and then ran a Sabol sensitivity test, so which is a variance-based sensitivity test where it can list, rank the variances offered by each of these, inputs. So for this one, we did use a quasi-random sequences because, Monte Carlo simulations are run for like 5,000 to 10,000 runs to get a good data set and then start doing analysis. But Medallica models, we have to understand the underlying computation of it. So it's like, we can't run 10,000 and 20,000 simulations with our Medallica model. So we went with quasi-random sequences. So it offers, these are random sequences that can offer lower, quicker convergence. So we had to run around 400 to 350 to 400 runs to get to, for for mimicking the entire span of probability distribution. So that's what we want to get to, because we don't just want to have like a linear variation in the input profile. We want to consider the realistic probabilities that will be observed in real systems. So similar to the previous three coupled systems application, we also went from a completely disconnected community to a completely connected community, which is the community based out of Denver, Colorado. And here is what our power consumption profiles are looking like. So the power consumed by infrastructure systems, where the buildings were contributing to 57%, and the EVs were dominated by 27% of consumption. So since this is a futuristic community with 100% EVs in them, so that's why we see this dominant load of 27% consumed by EVs. But current communities, under the current conditions, we might not see such heavy EV loads. So this framework and the models also offer a way for us to test different EV penetrations or different renewable penetrations. We can start exploring systems and then start looking at percentages of different assets generation and consumptions based on the different penetration ratios. And when looking at the other interdependencies, so I've just plotted only the net energy consumption instead of plotting all the different assets, generation, batteries that you see in the first plot. So we do see there's a 28% reduction in energy because we consider all the interdependencies together. So if we don't consider it, we would be overestimating our energy. So that what it means. And also we do see during the peak periods, right, like the commuting hours or the early in the morning. So that's when there's larger differences between the baseline and the interdependency cases. That's what we saw. So this is not just going to be a 24-hour simulation, right? We want to understand multiple days or multiple hours, multiple scenarios of inputs. So what we did was, to run this Monte Carlo simulation, we introduced some stress signals, which are varying occupancies, varying price signals, varying communication packets into these residential blocks, usages, and then there's road thresholds and packets per person. So all these were introduced into the model as probability distribution, so we can generate a larger data set to understand which is the most influential interdependency among these. So here is what we see in terms of community energy when we simulated the models with stress signals. This is the entire, these are violent plots, so which shows the probability distribution of all the 400 cases that we simulated. And so we do see the means, like, most of them are lower than the baseline, which is the decoupled system. So because, of course, because there's more people that are stagnant on roads, there's loss of packets, so there's so many things that are contributing to this lower consumption. And here, among the human mobility, transportation, travel time, and communication and transportation, all were looking very similar. But when we looked at the cyber delays, where this is delays in the control signals reaching the controllers, so where although it had like 2% mean variation, but it had a larger variance. So it means that sometimes it just not puts the controller to take the right decision. So there's a lot of controller impairment happening in the simulations. That's why we were seeing larger variance in energy consumption, difference in energy consumption. And also the EV charging profiles, because of those probabilities where people are responding to electricity prices and also state of charge, we were also seeing a 31% variation from the baseline. And also this had a huge different profile, very skewed profile, and also the standard deviations were really larger. And eventually, when we ended up putting all the interdependencies together, integrating them in the models, we started seeing the global interdependency, the energy consumption, although was deviating by 21%, the profile of the distribution was looking more a normal distribution. So this also signals that the system is becoming more and more a natural system, because that's how it is. Natural systems are more fit into this normal bell curve. So what does this mean to the power grids? The direct, similar to what we talked about in the previous case, there's this direct impact on the real-time unit commitments. There's pricing, and then the generators have to start producing more energy, generating more power, electrical power. And then there's also going to be changes in the new, locational marginal prices, because the generation, and we are calling in emergency generations at times. And also, this could in turn change how the EVs are going to respond to the electricity price, because if the prices are changing. So it's more like a cyclic, changes that's going to happen. So these are very, very essential when we are modeling these interdependent communities. As we want to we want to understand exactly how much we are going to consume, rather than oversizing or overestimating. So it's better to go with these interdependent models. And when we did look at the sensitivity, right? So we finally went about looking into the correlation study, also looked into, ranking which interdependencies are most important and most effective on the energy consumption profiles. The correlation study did not give us a larger, understanding or trends, but it did. Like, we could see, what thresholds the community will start seeing outages, or what threshold we will start seeing heightened energy consumptions. So all that was visible from the correlation studies. And also, if at all, like, we are seeing at that threshold, it can give us insights on, when to upgrade the community, or which is a breaking point. So that's something that we were observing from correlation study. And also, when we looked at the sabol indices that were generated from this large quasi Monte Carlo data, we were seeing interesting trends where sabol outputs something called as a first order effect and total order effect. First order is something called is a direct effect, where one of the parameter, which is the input, say it's the electricity pricing, how it impacts the output, which is the energy consumption. So that's the direct impact of the parameter on the output. But the total order effect is all the direct effects, indirect effects, all the cascading effects. All that together is what is called as a total effect. So here we were seeing that the occupancy had larger direct impacts, and then the packet data, that we were considering, that also had a direct impact. But there was two interesting ones, like indirect effects were dominated by these occupancies that we were considering in the models. And also the road delays were also responsible for, influencing all other parameters, right? Because there's no more people stagnant on roads, the EV charging happening at the blocks change, the number of people entering the blocks change, the human driven electricity consumption of the blockchain. So all these were dependent on few of these, like the road delays and the occupancy. So this was influencing all other parameters, and these are very critical when we're modeling. We also considered, looking at the second order and third order, fourth order. So these are like cascading impacts and effects that happen because of each of these parameters. So we try to visualize it. So it was looking more like this, where the road travel delays were impacting the occupants and EVs. EVs were impacting charging decisions, and then so we did trace like all the parameters together. So it gives a good understanding of how this community is set up, and what is going to impact more. And we also have to understand that it's not just these systems that are going to be the major impacting ones, but for the community that we have modeled, these are the ones. But if we are going to trace more relationships like water and energy, if we trace more relationships in the model, we're going to see a different importances, and a different interdependency being the dominant ones. So in conclusion, this work together is, the three different explorations and applications. Is the first to model this cross-domain infrastructure interactions in one of the modeling platforms. Previous studies were mostly like standalone two sister systems, that were also the commercial tools were limited in these multi-domain interactions. And this study also quantified the sensitivity of these complex interactions that are essential to be considered while modeling these systems. And also, this SEC library will act as a tool to do co-design and optimization of these future smart connected communities. So where is the future for SCC library? So there's a lot more we can do. So we just started. There's more to integrate. We can do resiliency studies with this. Newer extreme weather profiles, uncertainty distributions, and then we can also trace and add more failure fractions, how quickly systems can recover. Like, if a microgrid fails, how quickly can you get back? So all those kind of studies can be done with these models. And then there's also hybrid energy systems that we can model in communities, like geothermal or other fuel cells, and a lot more. And then there's ways we can use these community modeling approaches to do some inter microgrid grid resource sharing, energy trading, and a lot more things can be done. And then EV to grid integration is something that can be done using these models available. And here is our project website. So if you want to know more details about this work and publications and any of the collaborators, and then some of the historic green village and the data and all that, so you can have a look at this project website for more information. And finally, I want to thank NSF for the award, the funding, and also the previous developers of the SEC library who put together this initial version of it. And also, if you have any further questions about the library or access or the work, can reach out to me, Dr. Zuo, or the new students who are going to be the future developers of SEC libraries. And thank you so much for hearing through. And yeah, happy to take any questions.
Thank you, Saranya. Yeah, this is really amazing. Especially, I like that you start to aid your experience from industry practice to justify or to explain why we do this kind of modeling. That's just really nice. Okay, any questions from students? Yeah, I know it's a little bit out of our architecture engineering domain, but I would say, as you can see, with education you guys get, you can do way more than what you thought you can do. Right. So especially energy system, it typically now everyone talking about beyond the buildings, community, microgrid. That's something the Modelica can help you to do. Also, any question from the online audience? Okay, we have questions. Sarani, you can read the question. So.
Okay. So there is.
How did you implement the quasi-random sampling in Modelica?
So quasi-random sampling was implemented in Python first, and we generated samples, and then those input files, it was converted as input files with different data sets, and then it was passed into Medallica to do multi-simulations.
Did you use FMU or you just use the building spy?
It was through Building Spy for this work. So it was the data sets were generated externally, but there's also ways to do random generation and then do random sampling in Medallica that can be that can be useful too if you want to model some stochastic behaviors, like occupant probabilities or anything. We can do random generators. There's seeds, and I think it's in the Medallica standard library that can be used.
Yeah, just for your information, if you're interested in take advantage of Python, there's two options. You can do. One is using the Buildings Py. It's also developed by LBL. It's part of the Modelica Buildings library. So that allows you to use Python a lot of functions, then connect to the Modelica model. So then you to do different things. But in that case, you have to have your Modelica software running, executable. Then another option is export your Modelica model in function mockup units as executable. Then you can call it directly using your Python code. So that's two options. We are using both of them in our lab. Okay, Sarah, there's another question.
Yes. So regarding the sensitivity analysis for cross-domain interdependencies, especially the second order effects you demonstrated, how can this framework be expanded to incorporate infrastructure systems in developing countries where critical networks like water, transport, and electricity are often operate in isolation rather than as integrated system. Um, of course, we can, model individual systems as we showed in one of the decoupled examples. We could just do standalone modeling using the, individual system models we have. But the entire idea about that is that like these are interdependencies that you don't generally see it, like it's not visible in the real world operation, but they exist. So that's what we want to highlight. Of course, you can use it.
Yeah, I also want to add a comment. So basically, this is a very complex system to develop this library. So also to trying to validate the model we developed, we take a approach that we first develop individual systems, just standalone system for energy, transportation, or water network, as Saranya is showing there. And then we test them, make sure the individual system model work. After that, we sort of couple them. So in the library, actually, you are able to use those models as isolated system for your purpose. And then you can also modify, the coefficients of the model to fit into your system. Just for your information, we have another project we recently completed. This is a joint work with Indonesia. So a few of my students are led by my master student Nathan Kutz. So he implement a Modelica model trying to simulate a community which has PV generation, then provide power to pump to power the water pump, which can provide water for the aquatic systems, but also the water for the water tank. And then they use that they pump the well water to the tank, then use the water to supply for the community. So this is really for Indonesia. So you can refer Nathan's paper. I think Hongju, maybe you can find Nathan's paper and post it on the chat window. Okay, any other questions? Okay. Thank you for the kind of words. Yeah, we're so happy that this is useful. So the way we planned our lectures really start from the more basic buildings, then all the way to the future oriented smart city. Yeah, hopefully that can be useful for some of your research. So all the presentations and the recordings and the slides are available at our lab website. So you feel free to download the slides, and also all the related papers are also posted on the website. Okay, you guys have anything? Do you want to ask any question about industry practice? So one is right now designing I think maybe you can introduce a little bit about your work right now. I think it's
Yeah,
interesting.
I don't know how much I can say, but yeah, I can talk about a bit on so we are doing getting into transient modeling and simulation integrated into industry practices, where pretty much earlier it was all steady state tools and some amount of softwares and simulators we were been using, but to do some integrated modeling we certainly need some tool like Modelica to be used. And that's where all the applications on geothermal district energy systems, where we also have we have the bore fields, we have waste heat integration, sewage waste heat recovery. There's a lot more that can be integrated into this network of demands. So that's where that's something that we've been working on. And also data centers another focus area, where cooling and power systems is integrated modeling of these systems is very essential. And not just sizing them, so there's you also got to test if the sizes make sense, and like if they're if there's some kind of a failure or some kind of faults, can the system recover back quickly? So that is something that we are focusing on for the cooling and power systems. Yeah.
So yeah, excellent. Yeah, so some of the work is also related to Dr. Michael Waiter mentioned, right? So using Modelica to design the uh, fifth generation energy systems. Also, data center, we had a lecture earlier, and also a couple of my current PhD students are also working on data center modeling. Okay, question from Victor. What's the next for this series? We probably will plan for next year. That next fall, hopefully I'm going to teach Modelica again. So maybe we can have more guest lecture, extend topics. Maybe some of your students, if you guys apply Modelica in your work, you can come back give a lecture. Yeah, I think I can see now more and more people using Modelica. I'm definitely want to extend the topics for the guest
Yeah.
lecture.
I think everyone is seeing a benefit of using these, highly customizable modeling approaches than sticking to something that's like, a commercial tool where you're logged into vendor, whatever is available, right? Like whatever they release, that's what you get. And that's something, yeah. But also, these commercial tools are well tested as well. But Metallica's buildings library is like highly validated, but we still need more open source libraries and that are more validated, well tested with good documentations. So that will help the industry grow together.
Yes, excellent. Okay, one more question, Sonia.
Yes. To what extent can your model predict infrastructure failures or outages before they occur? And what kind of data inputs are more critical for accurate predictions? So right now, some of the models are simplified, but the way we are trying to say if the system fails is based on some thresholds. So in the power systems, when we were looking at the line and bus safety limits, that was from ANSI standards, or you can get it from IEEE, and then it's more like post calculating and then trying to see if you're hitting that limit or you know crossing those thresholds. So that's how we've been predicting it. So it depends on how you want to set up this model, and also the kind of data. These systems, it's been little difficult for us to get some data and information to validate these future systems because we don't have them yet. It's not like there's not 100% electrified community, and then there's not a community where you can get the data for charging behavior and all that. So um, it will be a little challenging to get most of the inputs. So far, we've been looking into hypothetical, but if there is some large data set available, it will be really useful to make this more work more realistic.
Yes. Yeah, I also want to add a comment. As Anya said that, the Modelica model is so realistic, right? So that recently I did some study trying to simulate a commercial building with a boiler. Then my simulation stopped, after a couple of days simulation. Then I realized, then I started to debug and realized I undersized my boiler, so therefore I caused trouble. So those things can help you to find if the system designed correctly. Another one is the control tuning, which is really helpful. So the tune of the PI loop is so difficult in the field, but using Modelica, you can do the exercise and you can see how you make system more stable. We have also another ongoing project is to use the Modelica model to support the fault detection and diagnostic of data center cooling systems. So this is a new project we just started last month. But of course, in that case, we will need to try to develop some faulty models, scenarios insert into Modelica so that we can predict those things. Okay, yeah. So next question to you.
Yeah, is there any scope to use this library to integrate with renewable energy systems like PV in district scale? Yes, for sure. We can, it's about modeling PV array. There are components available in buildings library which can simulate your, the series and parallel arrays of PVs. Then you can certainly model it. It's up to us to scale it, right?
Yep.
Can the big data optimization approaches be extended to construction planning, especially for resource allocation, material management, and sustainability evaluations? I'm not very familiar with construction management. Dr. Zio, do you want to talk about that?
Yeah, I'm not familiar with that either. Yeah, I think it probably difficult. But I don't know if anyone developed. Okay, so let's say the principle Modelica is equation based, right? So as long as you have mathematical equations, you can implement in Modelica. But I'm not aware anyone who implement any construction management model into Modelica.
But there are big data. I think some of our Penn State PhD students, they have developed data-driven approaches to do some effective planning, and I've seen some of the works previously, but I don't remember exactly who performed it. But it certainly would be good to look at Penn State's repository of research, like the thesis works. You might get some thoughts on that.
Yes, yeah. Our department, we have a very strong construction management group here. Of multiple faculty who are really expert. I know people are working on big data, AI. Definitely, you can come to visit our department website. You can find my colleagues' profile and check their research. You probably find something. Okay. Any other thoughts or questions? If no, then thank you everyone for attending the lecture. I hope all of you enjoy a wonderful, winter break. Okay, bye bye.
Yeah, thanks everyone. Thanks for the opportunity. See you all.